Okay, we can go ahead and begin. If anyone on Zoom can give me a thumbs up that they can hear me clearly and well. Thank you, Yohan. Start. Okay, good afternoon, everyone. Happy Monday. So, to speak a little bit of course logistics, um, homework one was due yesterday, I think. Um, how was that? Was that challenging? Was okay? Pretty straightforward. Straightforward. The guidelines are straightforward. Okay, that's good. Yeah, most of the homeworks are straightforward and they're coming directly from the slide. So if you refer back to the slides of the lecture, you would be able to find the solutions. Is anyone going to the career fair on Wednesday? Maybe? Okay. Okay, cool, cool. You're a IT or a CS major? Okay, interesting. Okay, so yeah, if you aren't aware of that, there's still time for you to go, I think. And it's highly beneficial that you go. Okay, so where are we at currently? We're in week 7, and we're in the transport layer as a chapter itself. And today we will talk more about the transport layer itself and the various tools that are going to be there, or the characteristics. And one of them is going to be um, uh, the reliability of data transfer within the transport layer itself. So that is very important when it comes to the idea of the transport layer. So just briefly, last week we talked about we gave an intro to the transport layer itself, and we talked about what does it do as a protocol, how it is separate from the other layers, and we talked about multiplexing and demultiplexing, which are the two ideas that are very common and we use in our daily use. So I just want to do a brief recap. I'm not sure why the mic. Okay, should be okay. Still not working, but so our goal was to understand the transport layer and what it does, and it's basically a logical means of communication that we have that would provide communication between two applications that are using two different devices that are using many different processes and how that is getting transferred over. So we said that the sender would break the application message into segments and pass it to the network layer that would use the IP address and transfer it to the other side, or it could be the client or the server, depending on what phase or what structure we're in. And the receiver would reassemble the segment layer, de-encapsulate the message itself, and pass it to the application layer. And we said that there's two protocols that are involved. Today, we're going to talk more about the protocols. We covered them slightly with demultiplexing and multiplexing. Here, we gave the analogy of the transport layer and the network layer and what they do. We said that the network layer makes sure that the mail is transferred from one house to another, but the transport layer makes sure the mail that is being sent is received by the correct person or correct kid that is in the house. And here we talked about the idea or a visual of how it works exactly. We start and always at the application layer. We have a message, a payload that is passed down to the transport layer message layer itself, and then we determine segments or values that would go on top of this message. We would create a segment, and with UDP, we said we don't use IP addresses. We just use the port number, the source port number, and we pass it down to the IP address. The receiver would do the same, and here's the idea of demultiplexing, which we have this specific message, and we do multiplex it to the application or the processes within the application. Here's the idea of multiplexing. If you're on a Wi-Fi infrastructure and you have multiple clients, or you're a client yourself and you're running many applications, this is the idea of multiplexing, where your request in the transport layer would be condensed or combine into one, and demultiplexing would distribute these processes or those certain applications. Here we talked more about like an application with two clients that are using the same application, because we said there is people that would search or users that would search in real time. And we gave an idea and analogies of these multiplexing and demultiplexing. We talked about the sockets and the processes. We talked also about the header, the segment format, which we go more in detail about today. And this is UDP. We said that we are using only the port numbers. So the process that is going from P3 to P1 would use the source port number of the server, which is the destination port of the server, which is 6428. And then it would use the source port that it has its own is 9157. We said that this the port number of the server remains the same, static, such that it's pingable by other clienteles or other users. When for the query reply, we use our own source port, which is the 6428. This is the reply from the server back to the client. So it would just do the reverse of the port numbers. For TCP, we said it not only uses the port number, it uses the IP addresses as well. So that's what we have to keep in mind. It's a 4-tuple transport protocol. So here, not only are we using the port numbers of the host and destination, but we are also including the IP addresses. And this was the summary. That's where we ended off. So multiplexing and demultiplexing, UDP and TCP. So today we are gonna go and talk about, we're gonna continue the transport layer. And the idea is that how we are looking out in terms of the modules is that we are gonna wrap the transport layer, and then you're gonna have a dedicated week for the midterm. We will not have lecture that week. So you can use that time to study, go over the material. But I will release some sort of idea about the midterm, what it will be, and the contents that it contain. And then you'll have a dedicated day for the midterm. So for the timeline of the midterm, we are looking at the week 3 of October. So October 20th, within that week, I will post a detailed announcement regarding the deadline or the exact time once it is finalized. But that is it. So you have the programming assignment due this upcoming Sunday. Then you won't have any assignments due till we have our midterm. Then we finish the midterm. Then second homework and the third homework will be to the second phase of the semester. So we'll have 2 more homeworks, and then we will have a final, and that is it. Okay. So any questions? Any concerns before we start? Okay, go ahead. That's good. So we move down from the application layer to the transport layer. So the objectives for this lecture is to understand the role of UDP more. We're going to talk about today what is the connectionless transport protocol. We'll explain multiplexing and demultiplexing again. We'll learn how UDP handles integrity and checksum. This is like a majority of the lecture today is checking the checksums for errors or packets that are getting sent, and how we can detect if there is an error between the sender and receiver. We'll recognize the limitations of UDP error detection, and then we'll transfer to the RDT, which is a reliable data transfer, quote unquote, TCP, but we are gonna build up to it. So as known, I don't know what this mic is not working. Okay, this is better. Okay. So as known, the slides are being, a portion of them is being used from the book, and that can be found there, and also that the lecture is being recorded. Okay, so the roadmap for the chapter that we have is, this is the roadmap. We cover transport layer services, multiplexing and demultiplexing. And today we'll talk about connectionless transport, UDP. So a summary from the last lecture is that we have demultiplexing at the transport layer is really about deciding which sockets should receive the incoming segments. And once the segment arrives, the transport layer would look at the header information and direct it to the right processes. And then there are two main protocols, the UDP, where the decision is only using the port number, and the TCP is using the source and destination IP address and port number. So this allows like TCP to handle multiple connections between the same pairs because it's an open communication or open handshake between the server and the client. And multiplexing and demultiplexing would combine the outgoing data, and demultiplexing would deliver the incoming data to the right sockets. So these all occur at the transport layer, but obviously the other layers are involved. So we will see these ideas getting repeated over and over as we go more in depth. So now we're going to talk more about UDP. So UDP in general, we know that it is unreliable, connectionless. It has a few differences related to TCP and often called as the bare bones, meaning that it's just very simple and provides best effort delivery. This means the packets could be lost or it could be delivered out of order. There's no congestion control. There is no order of delivery, whether the packets come in turn. So some packets that are getting sent later can be received first. So there is no order of there's not an order strategy that we have. So with UDP also keep in mind there's no handshake between the receiver and sender. There is no acknowledgement of the data getting sent, and there is no acknowledgement of the connection before data is getting sent. So each segment is treated independently. This question came up and we have answered it before in the application layer. Why is there a UDP? And we said that why do we need an UDP if it is so simple? And we said for several reasons. It is very efficient, very quick, and we have uses that are intended for UDP and can use or benefit from UDP, such as video broadcasting. Also, sometimes some games where integrity of the data is not so important. And so there's with the idea of there's no congestion control, it can send data is very fast. There is no delay or latency. So it is fast and useful for certain applications, not all applications. The uses or like certain scenarios that UDP is useful in these is like streaming multimedia apps where some package loss is okay, but the timing is more crucial, such that if we are watching a video, we said we need it to be efficiently and in a fast way to be sent to the user, but there could be some jitter or some buffer, but we want the video to be repaired or the quality to go back in a very time matter. Also DNS lookups, SNMP for network management. This is also we're going to talk about more in depth today, and even HTTP/3. So all these applications we can, if we take a look in depth of each one, they can all tolerate loss or benefit from low delay. So reliability is required on top of UDP. That's why it can be added to the application layer, like retransmission or congestion control can be built there. And that is what HTTP does as well. It builds reliable data transfer for over UDP. And we might not have covered that in detail when we talked about the HTTP part of the application layer, but that's what HTTP also does. Whenever you see an RFC with a number, that is basically formally defined protocol. So when we speak about wireless Wi-Fi networks or wireless networks of communications, we have ZigBee, we have ANT+, and these are basically protocols that are defined by the IEEE, or it's defined by the backbone of the internet, you could say. So basically, UDP was formally written in 1980, and it is one of the simplest protocol specification, and it's not very long. So if you want to read it, It's only 3 pages long, which is very unique in compared to other protocols or other mean of wireless communications. The way it's structured, we said we have the source port, destination port, we have the length and the checksum followed by the payload or the data. So you can skim this on your own time. If you just type in UDP or RFC 768, you can just go directly to it. And the source port would be our own source port, destination port. If we are pinging a server, that would be the port of the server. The length that is usually in bytes, and the checksum is something that we're going to cover more in depth today. And then we have the data, the payload. So this is kind of a little bit from the old slide, how the interpretation between a sender and receiver using UDP. So here we are using SNMP, which is a simple network management protocol. And it's basically the client is the monitoring system. It sends requests to check the status of the device. So the server or the agent in this case scenario runs on the device that is being monitored, like a router or a server, and replies with the requested data. So here the idea is similarly to the last lecture, it would start at the application. And this is going to be the message that is passed down to the transport layer. The transport layer itself would use UDP here in this essence, and it would send it to the IP address or the IP layer. Then it would go to the link layer, and then also it would go to the physical layer, and it would transfer on a physical median, or could be a wireless phase with electromagnetic waves, and it'd be sent to the server. So let's look at more in detail. So last week we walked of a general example of the transport layer. And from the sender perspective, we saw how the message is getting handled. And here the same idea is getting done, but here we are focusing more on UDP of a sender. So the process is very simple because we don't have to make connections. And we've seen that with like the connection, the idea is that we ping the server and we make sure that it is being connected before we reach out with the request. So let's see a step-by-step of how this works. So the first thing is that the layer it starts from the application layer. And in this case, this is like a request that is being requested. And then we would send it to the transport layer. So next, the UDP as a segment would determine the values for the headers, which is like the source port, destination port, length, and checksum. Then it creates UDP segment by attaching the header to the application. Then it creates this segment that we have showed or entailed of what the bodies consist of. And then finally, this is passed to the IP layer to deliver across the network. And at this point, the data or the segment itself is ready to be transferred. So we would transfer it to the other side, and now it's transferring to the SNMP clients. So it would travel from the IP address or the IP layer itself to the physical aspect. So on the receiver side, it is the same thing as the last example we talked about. It would receive the segment from the IP layer of the server. This is the raw data that is coming up from the network. And then the UDP itself as a protocol would do the checksum. And the checksum idea of the checksum is we're going to talk about here in a little bit. But this is basically checking, saying, hey, is this data belong to me? So there's some way of checking the data integrity in that sense, but it's not very reliable and compared to TCP to say, hey, does this packet or does this segment belong to me? So there is a way of checking with UDP as well. So if it is valid, then UDP would extract the application message, a layer message from the segment, and then it would deliver it to the application of the client. So that is the idea. Very light, easy process to do. So the UDP segment header that we have here It is very small compared to TCP. It is only 4 fields plus the application data. So we have the source port and destination port. This is where the message is coming from and where it should go to. The length is the total side of the segments and bytes, plus the data. The payload itself is whatever that is getting sent from the client or getting sent from the server back to the client. And this is the checksum that we're gonna talk about here more. It is a way to check if the packet does belong to the actual user or not. So that is what it consists of, the UDP. This are the only fields that are included in the protocol, the RFC protocol, and included in the segment header itself. So the information that we will talk about now is going to be included in various aspects in the IP, in the TCP. So we're going to look at how the checksum is actually calculated, because this idea is important. Just if you can pay attention here, because this concept will get repeated over and over across the layers. So UDP checksum, and we said this is the way to detect errors, like that are flipped in bits in the transmission segment. So we want to walk step by step and see how we can detect the errors and how that works with UDP. So suppose I want to send you two numbers that are 5 and 6. Along with those, I want to send you also the sum, which is 11. So during transmission, I am sending you, maybe I'm a server, or I am a server and I'm sending you a reply back to you as a client. Now during transmission, one of the numbers gets corrupted. Instead of receiving 5 and 6, you receive 4 and 6, plus the checksum value, which is 11. So the checksum value here that you received is correct, but the first and second number is wrong. Obviously, these numbers are very small here because we are dealing with a small scale of an example. We will look at a higher scale example in a minute. So what you would do is you want to check, you want to add the numbers to make sure that you are getting the checksum that I originally inputted or intended to send. Then you would compare the number against the checksum that was sent, and you see that they don't match because you should be receiving 5 and 6 and the checksum of 11. So 4 and 6 is obviously 10. So there is something that is being wrong here. Since they don't match, this tells us, hey, there was an error during the transmission, and that is the role of the checksum, is to catch the corrupted data. So this is a way that we will make sure that when the segment is being passed during transmission, is we can rely on this checksum to say, hey, if the segment is reliable or should be sent to us or not. But there is some flaws with the checksum that we will look at in a minute. Now you might ask yourself, how can this happen? How can this error occur, or like the bits that are getting flipped during transmission? And there's various causes for these that this lecture will not cover more in detail, but it could be electrical noise that is on the wire. You have, maybe if it's wireless, you have interference noise. You're going through various, you could say, obstacle or physical interference, such that those noise are getting flipped. For wireless interference, we have Wi-Fi signal disruption. Also faulty hardware or cables is another example. So the example here we have is the application sends data. UDP would check the checksum of that segment over the network. If the bit has change in transit, the receiver computed checksum would not match the sender checksum, then the receiver would discard the corrupted segment and say, hey, it needs to be sent again. Actually, with UDP, there's no source of acknowledgement with that whatsoever. So there is no way we can say, hey, send it again or something like that. But the data would not be sent. Okay, so the goal of the checksum, obviously, we said it's to detect the transmission data that is being sent. and it provides a basic way of integrity, not the best way, but we want to make sure what was sent is received. So it is a light way of a method. No need for retransmission at this layer. We have the sender side, obviously, and we have the receiver side. So the UDP segments on the sender side is treated as a 16-bit numbers, including the header and the data, which is the payload. And the sender adds them using one complement arithmetic. And then it would give us the result checksum that is stored in the UDP header before the segment is sent down to the IP. So we have the application, we have a specific request with the application, it gets sent to the transport layer, then the segments get created, and part of the segment header is the checksum. And we would do, the sender would add all the bits, and we have an example of that, and then it would send it to the receiver. The receiver does the same checkup calculation that was being intentionally sent from this receiver. Then it compares it to the results to see if the checksum value inside the header. If they match, an error is detected. If they don't match, then no error is detected. Maybe, but what could happen is that if they match and there's no error detected, which is in rare cases, some errors can still slip through, and we will talk about this now. So here's another example of the internet checksum as an example. So here is we are show the internet checksum on how it's actually computed using two 16-bit words. So each row represents one 16-bit number, and the checksum is calculated by adding them together bit by bit. So first thing we do is we start adding the rows. So we would add each column in binary. So 1 and 0 would be 1. 1 and 1 would be 0, but we carry that 1 onto the next column. So 0 and 1 is always 1, and 1 and 0 is 1. 1 and 1 is going to be 0, but we carry over that 1. So then we have the next column 0 and 0 plus that carry, it would turn into 1. So the same idea gets repeated. When you have 1 and 1 would be a 0, and there would be a carry on. So if the next numbers that you're adding are zeros, it would transform into 1. So that gives us the initial checksum that is shown on the third line. Then after, what we do is we do our wraparound. So because we have a carry bit on the far left, and because we are restricted to only 16 bits, and that adds an extra bit. So that wraparound is added back to the right-hand side. So the key part of the internet checksum is arithmetic. So after adding the carry-on that we have, because we have a final 16 bits that we deal with. So if there's a carry-on that is gonna go back and being added and gets added. And then we have the checksum result. We take the ones complemented of the sum. So that means we flip every bit. So the zeros becomes ones and the ones become zeros, as you can see. So this is the checksum. We have all the zeros are getting turned into 1, and the ones are getting turned into zeros. And the flipped value, or the checksum, it is what is being stored in the segment itself. So at the receiver, the same process would happen, and the receiver would add everything up. If the total number is all in ones and the data is valid, then then that data is successful, or we can verify the checksum. If not, then there is an issue that is going on, or there's an error with the segment that is being sent. Here, I want to show you why the checksum is a lightweight method and why it's not the best method for us. So why it's not perfect. So here we have bits that are being flipped. So imagine we already computed the checksum for the 216 bits words. And now during transmission, 1 bit, which is the first number, is being flipped from 0 to 1. It was originally 1 and 0, and it got flipped into 0 and 1. And we have a second number that got flipped from 0 and 1 to 1 and 0. So both numbers are corrupted, but in different ways. Then obviously we would do the wraparound if we have a one that is getting carried to reach that final 16 bits. And then we have the sum and the checksum, which is the opposite of the sum where we flip all the zeros into ones. But here's the problem is that when you add these corrected numbers, the +1 from the first flip and the -1 from the second flip would cancel out. So the total sum would not change. So that to the receiver, it looks like there is nothing wrong, but in reality, two bits got changed. So that's why it is not very reliable or a weak protection system. So it is not the best. So it is not foolproof. It can detect errors, but certain patterns like pairs that are getting flipped or pairs or bits that get slipped through would not be able to detect it. We will see stronger error detection methods like CRC that don't miss these special cases, but that is usually for UDP. And we said that UDP is not reliable whatsoever. So that's why TCP is more optimal and more beneficial and better for us. So far about UDP, it's a no-frill protocol, so segments may be lost or delivered out of order. We know that. Delivered out of order, meaning there's no way of controlling the order that the packets or segments are getting received and sent, and segments may be lost. That could also be a possibility. So it is a kind of a way like send and hope for the best. So there's no any planning or any back end or a response plan for UDP. But it does have some advantages that we are saying that is efficient. There is no setup is needed. No runtime chirp is incurred. So it is very quicker and lightweight. And it can function with the network service is also compromised. That is also a thing, something that is useful of that. And also provides a basic reliability checksum, not optimal because we've seen that there's a flaw with the bits if they get flipped and then interpreted. So the application needs more than what UDP offers, extra reliability and control, such that we have many segments that are getting sent and we want to control the order that they come in. That's why TCP is a lot reliable. And we're going to use a finite state with TCP to make sure we have different state transitions. In transition, from each transition, we have a confirmation that gets sent between each transition. And we said that HTTP is building on top of UDP. So they are incorporating reliability on top of UDP as a protocol. Here we're talking about the principles of reliable data transfer. We haven't moved over to TCP just yet. I want to show you how we moved from UDP and how we can solve the idea of the flaws in UDP to make it more reliable. So we will talk about the principles first, and then we will make our way into TCP. So that wraps up UDP. We looked at the action, the header, and the checksum, and we want to talk about reliability in a generalized way. So the question that should arise to you is that how can two devices or two clients or a server and a client communicate reliably over a channel? How can we make sure that the data is being sent in order in a timed fashion manner and the reliability of the data cannot be lost, corrupted, or sniffed? So sometimes when you are, to give you an idea of principles of a reliable data transfer, is that sometimes when you are texting a friend, could be on iMessages, could be on WhatsApp, any social media app. When you're texting a friend and your messages don't get delivered, or sometimes they arrive late, or they show up out of order, sometimes you sent a message and it doesn't get sent, and you send another one, the order would change. To stay in sync, you would communicate with your friend, hey, did you read this? Or he would reply a question mark or something like that, where the communication itself is not very clear. So that is to get you to thinking about TCP, how we can make sure that we have an optimal way in the transport layer to do that. So we're going to start with a very simple model of unreliable channel and build up step by step, and we see how the reliability is achieved. So here's the scenarios that we're going to consider, and we see here, we have the server as usual, and we have a client, and obviously the application is sending a process that is something that is related to the application. And that process that is getting sent has data that is attached with the application, with the process. And we need a reliable channel that would transfer the request to the server. So for this moment, I want you to imagine we have a perfect reliable channel. So there is like no losses, no errors, no reordering. This is like abstraction of what applications wish they had, so that the sender hands down the data and the receiver gets the same data in the right order. Also, one thing to notice in this specific model, it is only one directional. So data flows from one sender to receiver. But we want to later expand the idea of that. We have a two-way communication, means of communication, and that is TCP. It is not just a one-way, but right now we have a one way of communication and we have a perfect reliable channel. And that's something that we wish to have, but it has to be worked for, or we have to see how TCP becomes itself. So we talked about abstraction, which is like we have a reliable data transfer that is optimal. The data gets sent. We have no issues whatsoever. But in reality, and when we come to the real world, or the idea of reliable data transfer is that the network itself is not very unreliable. So we know that packets can be lost. And we talked about that maybe in the idea of the buffer of the router. We can have a buffer overflow and the packets can be lost. Corruption as well, or reordered. So to achieve a reliable data transfer, we need a protocol that runs on the both sides of communication. So we have a sender and receiver protocol boxes here. On the sender side, the idea remains the same. The data is being stored and it is being sent to the receiver. The receiver would accept the incoming data, checks it, and delivers it to the correct application. Now we said in the last slide is that we have a reliable channel, and that is the perfect goal, or what we are aiming for. But here we have an unreliable channel between them. So how can we make it reliable, and we can make it more something that is dependent on, or advancement of UDP itself? So even right now is that we have the application sees only a one-way flow from the sender to the receiver. Under the hood, it is running bidirectional. So we have an arrow going from the data of the server and back to the client, or from the client to the server. So we have incorporated bidirectional data transfer, and we want to make sure our unreliable channel becomes more reliable. So this is the heart of like the reliable data transfer. This is what we want to do. We want to make sure that we are sending data bidirectional from client and server, and from server to client. And we want to make sure that the data we are getting sent is reliably sent in order, and it's not being corrupted or interfered, and there can be like no loss in the data. So something to keep in mind, and obviously this is known in almost every problem, or when we build reliable data transfer protocols, the complexity of the protocol depends on directly of what kind of problems the underlying channel has. So for example, if the channel itself loses messages, then the protocol needs to detect that and retransmit it. If the channel itself can corrupt data, then the protocol itself must also use checksums to detect errors and request transmissions. So we are seeing the flaws that could happen in the channel and how we can fix those. If the channel can reorder the messages as well, then the protocol must number or name or label the packets so the receiver can say, hey, put them back in order, or this specific packet that is labeled is not being sent in order or needs to be resent. So the protocols like TCP, you see that in a big picture, or when we talked about it briefly in the application layer, we think of it as like the best process of transfer as a transfer protocol, and it is the best, but there's a lot of underlying that goes behind it. And these are the underlying that goes is the loss of messages, the corrupt data, and the reorder of the message. So going back a little bit to the human analogy that we had, and for us, it is very easy to see. We would look at the messages between the sender and receiver, and we can see exactly what was happening. We can easily spot saying, hey, Alice have communicated with Bob, and there's two messages, and we can go directly see that there's a message that is not being sent to Bob or Alice. So we can know it very easy visually and the human analogy. But from the sender perspective, things aren't just clear. The sender doesn't know automatically if the message is made across the unreliable channel. That is when it comes to the idea of building up to TCP. So if there's a current between them, between the sender and receiver, the sender cannot see what's happening on the receiver side inside the channel. How can the sender say, hey, well, I sent you a segment using TCP, and I want to make sure that you have read the segment, you acknowledged it, you made sure that it was properly read. How can I do that? And then now we just want to focus more about the sender itself. So everything the sender learns about the receiver has to come from explicit communications, messages that are getting sent between the channels itself. And that is the idea of the acknowledgement that we will have. Hey, I want to connect to send a message. The server will reply saying, yes, we are connected. Send the request, acknowledgement of the request, and that is the way of communication that we have added to TCP. So the idea is that here, this idea is more important, and this is the way of reliable data protocol before we design and we look at carefully how we can design a protocol that has availability or a set of messages that can be exchanged and coordinated between the receiver and sender. So this is the diagram that we will use for us to have that reliable data transfer protocol. This is the interference that we would have. So let's walk step by step. Obviously, first we would look at the client, and first thing first is we have the sender side. The application calls RDT/send. This is the app saying like, hey, here's some data. Make sure it reaches the receiver reliably. And that call handles the data from the sender to the receiver in a reliable data transfer protocol. And then we have the second UDT_send. This is once the protocol appears with the header, this is time to push the packet down to the unreliable channel. Remember, the channel itself cannot lose or corrupt packets, so reliability has to be handled above. And on the server side or the receiver side, we have RDT_RCD. This is when a packet arrives from the unreliable channel, the transport layer is notified through the RDT_RCD. So there is a ping when the data is being sent over, such that the receiver know there was incoming data that is being sent. And the last thing is to deliver the data back to the server. So if the packet is valid, we can use the protocol itself to deliver the data back to the server itself. This ensures that the app sees the clean intended message. Something to note here as well, we have bidirectional communication now appears, and this process would get repeated. So it is not just one bidirectional of a way. So both sender and receiver can exchange messages between over these four um, identifiers or ways of we can make sure that the data is being sent reliable in a more reliable fashion. And here we have data that is being sent. This is the payload data. Obviously, we know that it becomes a segment because the data is the actual payload that we deal with on the application side. And we also have the packet that is going from one side to another. That is the idea of layer 3, the networking layer. So this is the way that we can have a clear way of communication between the sender and receiver to make sure that the data or packets are being sent in a fashion order and a reliable order as well. So now let's start building the RTD or the reliable data transfer protocol itself. So we're only considering unidirectional data that is being sent, but keep in mind, control information will still flow in both directions. So for us to design a way or the specific protocol, we need to describe a way for the sender and receiver behave. And this is where the FSM comes in, or finite state machines come into place. So what we have is here, we have the first state that would happen. And this is the basic idea that the system is always on in some sort of state. This is basically a state that is being happening. That is basically the current state of where we are in the current protocol. And that represents like the condition of the protocol, like a snapshot of what it knows or what it's waiting for. Then we would have an event. This is something that would cause state transition. It would cause the state that we have into a different state, ideally a transition. So something happens as an event. It could be like a message that is being sent, a timer is expiring, or data that is being received. These events are what trigger the system to change the state, the current state that we have. And we have an action. This is when an event actually happens, the protocol would take an action. So this is like sending an acknowledgement saying, hey, I have received the data, or I'm creating a new packet, or delivering the data to the application. And then we have a new state that would appear, basically state 2. This would cause the system to shift to a new state. So the FSM is really just a set of states with rules for how events and actions drive transitions that between. So we have the current state, and once we have an action and when we have an event, it would cause the state transition, and the actions would take on the state transition. So the analogy is like to think of this or the FSM with the different states is that we have a light switch here, and whether it's on or off, this is the state that is currently in place. And the flipping the switch is the event, and the action itself is like turning on the lights. The lights would go on or off. So FSMs is like a way of us to describe the protocol behavior in a clear, structured way without being ambiguous or unclear. So now we talk more about RDT 1.1, a reliable transfer over a reliable channel. So we are beginning with the simplest possible case, making sure like the underlying channel is perfectly reliable. That means no bit errors, there's no packet loss. Everything is getting sent properly in a correct fashion. So We don't have to worry about corruption and loss if we have a reliable channel. We are under the assumption that we have a reliable channel for transferring. Um, so RDT 1.1 is just showing the mechanics or of sending and receiving when nothing can go wrong. So we have separate SFM messages and states or that would appear. We would use those in the sender and receiver. So the sender itself is in a state transition that is waiting for the call from the above. So the sender itself would wait for data that is coming from the application and passes it down. And the receiver FSM just waits for a packet to arrive and deliver it to the sender. So we have the receiver that is also in a state transition, and this is waiting also for a call from below. The protocol is here on the sender or the receiver is very straightforward. When we have an action or event, the state transition would change to do its right or intended action. So here the sender application, the sender actions appear where that we need to create a packet using the specific protocol, and this would push the packet into the channel. That's all the sender has to do. So this is the way of communication that the sender and receiver has state of transitions, and they are both in idle, or you can say they are in a waiting process until they get specific action from the layers above. And once they get a specific action or event, they would take place and send over the data. And the receiver is the same thing and would wait for a specific action from the sender, who would receive the data and then deliver the data to the right maybe it is the client or server, because the direction of the communication could be a two-way in this idea that we have. This is very easy because we are assuming that the channel itself or the RDT 1.0 is very simple, and we're under the assumption that the channel is perfect. We said that there is no bits, errors, no packet loss, and the sender receiver only need one state, since nothing can go wrong with this. RDT 2.0 is the channel with the bit errors. So up to now, we assume that we only have a perfect channel. We are building our goal based on the assumption of a perfect channel, but that is not realistic. In reality, we have the channel that can have flips of transmission due to flaws in the transmission links that we're sending the packet or the data over. So that is a problem that we could have. So the key question is, how do we recover from the errors themselves? And before we dive into the protocols, let's say think about how a human would handle the error. So we said that you were talking with someone and maybe it's on the phone, or it could be the messages idea or analogy we can go back to. And then you would say, hey, can you repeat that? Or sorry, what was this? I have misheard you. And if you heard it correctly, you would nod or give a confirmation saying, hey, I have received the data properly or accurately. So network protocols, they're gonna work the same way with feedback and communication and retransmission. So that is the idea we're about to formalize in RDT 2.0 is the channel with all these with all these characteristics. So in RDT 2.0, we're not under the assumption that we have a perfect channel. They could be bits that are getting flipped, packets that can get lost. So to handle this, we will use the checksum, so the receiver can detect whether the errors have occurred. But detecting is not enough. We need a way to recover, saying, hey, if we get the checksum and we have found out the packet does not belong to us, how do we recover from that? So this is the first acknowledgement that is being sent. Yeah, so this is basically saying that The channel could have flip bits and packets, and the checksum is a way to detect these errors. But how can we recover from the errors? So this is the acknowledgement that comes in, like the human analogy. If the receiver gets the packet correctly, we would tell the server, yes, I received this, that is okay. And we have NAKS, which is negative acknowledgements. The server detects an error, sends a negative acknowledgement saying that, hey, there's something wrong with this packet, we need it to be resent. So whenever we receive that negative feedback or that negative acknowledgement, it would transmit the same packet. This would ensure that if something was corrupted in transmission, the correct data eventually would get through. Remember, with UDP, we did not have these specific acknowledgements that would appear. So that is why UDP does not deliver data in a reliable way. And how it makes sure that the data is getting sent in a time fashion or in order uses a stop and wait approach. So the sender itself would transmit exactly one packet, then stops and wait for the acknowledgement. And we see this with when we did a little bit of the programming. We cannot skip a request until the request that we have initially requested gets replied to or received. Then we can go ahead and input another request. So sender sends one packet, there's going to be an acknowledgement or negative acknowledgement. If there's negative acknowledgement, the data would be resent. If it's acknowledgement, that means everything is good to go. Then we will wait for the receiver response. So this is basically how the RDT 2.0 works. In the next lecture, we're going to cover the next protocol or reliable data way of communication. We covered RDT 1.0. We were making sure that we have a perfect reliable channel. And this is not really realistic in our world of the networking transport layer itself. We talked about RDT 2.0, but there has been advancements. So this is what we're gonna cover in the next couple of lectures, specifically the lecture on Wednesday. And we have covered UDP, and UDP we have went over it very quick. It is very a lightweight protocol compared to TCP, a reliable data transfer. We haven't yet got to the phase of the actual TCP that is getting used yet. We saw the flaw with UDP, and we are trying to think like you can think of it like as a way of engineers, or if we have a problem and we're trying to solve it. So the problem that we had with UDP is reliable data transfer that is being sent, a way of transferring the data in a time fashion and way that the packets don't get lost. So we came up with this analogy that we can use acknowledgement and negative acknowledgements, and we use a wait and receive wait and a wait and stop approach, such that we send the packet and we wait for an acknowledgement. Then we would go ahead and do the next request. So yeah, that what we talked about is that so far UDP is very lightweight. Multiplexing and demultiplexing uses the port numbers and direct traffic to the right process. The checksum itself would help us detect errors, but cannot catch all the corruptions. And applications need more reliability. So HTTP3 must build it themselves, and this is what they're doing. And this motivates reliable data transfer. When we say RDT as reliable data transfer, we started with RDT 1.0, and that is perfect and extending to 2.0. But we have more to go over in the next lecture. So that is it for this lecture. We will pick up on Wednesday with the next lecture. And if you have any questions, you are free to ask them. I'm gonna stay here for a little bit for any questions. If not, you are free to go. And I will see you on Wednesday.
When I was putting my name into the email, I hit backspace twice because I forgot what my last name.
Okay,
There's like two of the weird characters, is that an issue?
no, that's
I
fine.
figured.
Yeah, because I don't want you to go resend it again just for that issue. And you see, we in class, how many times I messed up with that. So it's completely fine. Yep. Okay, I know,